Today I'll be sharing with you presenting to you my project on AIML, my AIML project. So the dataset that I'll be using or covering is on the house prices in Malaysia in 2025. So this is my original dataset that I have over here, and these are the different modules that I will be importing from sklearn, especially. And so I'll be doing data preparation and exploration. So first I'll read my CSV file. As you can see here, now I have some information about it. However, you can see that there is some missing values over here in my dataset, in my old dataset. And so I will find some of the null values, the missing values in the dataset, which is about 11. And I would extract out the index position of where it is, or where all the missing values are, or I can just find it using the table that I display here. So all these 9 values. These are the different rows that I have the missing values under median PSF column. And then I'll fill those values with the forward fill or F fill method. So the F fill method fills the value or the missing of the rows with the missing values with the value in the previous row. Yep. And I'll print the information again. You can see that there's no more missing values. And you can double check by doing a sum of null values. And also, I'll be dropping some of the features or columns that are irrelevant for my investigation. So I'll be dropping median price and transactions. I'll be just leaving the output feature that I want, median PSF column, and the input features, which is the remaining columns. And then I would also convert the categorical data into numerical values using the label encoder module. And then I would export this clean CSV file. So in the machine learning modeling, I'll be reading the new CSV file, and I'll be assigning my input features and my output features. My input features, as I've mentioned, is the township, area, state, tenure, and type. And my output would be the median PSF. And now we'll be doing some linear regression for unnormalized data. So we will have to split into the train and test set in the 70-30% ratio. And then we'll train our linear regression model, and we'll get these values, the intercept and the coefficient. And we will also get our MSE and RMSE for that model, as you can see here. And then we will we'll do linear regression modeling for normalized data. So we will normalize the data by using the min-max scalar, as shown, and we will find the intercepts and the RMSE and MSE value again. So you can see there's not much of a change, 43744, 43744 instead of for the RMSE value for a slight bit. Yeah. And we will now be doing a second training for the rich regression model. So we'll be doing it for unnormalized data. So we'll find the intercepts and the coefficients as well as the MSE and RMSE. So these are the values as shown. And then for normalized data for rich regression, these are the values as shown for intercept and coefficients as well as MSE and RMSE. Then following that, we'll be doing some hyperparameter tuning for alpha for rich. So these are the for loop, and this for loop basically will help us to from the list of array values will help us to give us the best alpha value and the best MSE and the best RMSE. This applies for lasso as well. So this is our best MSE and RMSE and the best alpha value for a rich model. This is the plot for MSE against alpha and RMSE against alpha. So for lasso, similarly, it's the same thing. For the normalized data, we would do a hyperparameter tuning. As you can see over here, best alpha value is 0, and these are the MSE and RMSE values shown. So we can see that based on the comparisons of all the models, we see that there is not much of a difference, and this may be due to the fact that the linear regression model may have already provided the best MSE and RMSE values. And another reason would be due to the low variability of the features in the dataset. Yeah, so this is my presentation. Thank you.